happening is detecting and also quantifying what is the coverage over there, how much you have. And so that plot of the change in angle versus time is what is called sensogram. And sensogram gives you the detection. So this is a very common tool in many biolabs, and you can commercially buy. And the commercially buy is a very simple device that actually, with the help of your friend in physics or electrical engineering, you can make it. But if you buy it, you're talking about $100,000. Very simple device where you have prism is coated, you have goniometer to scan the angle, the light going in there, but you can make it for less than $5,000 yourself. Okay, so a lot of money goes into computer control. You know, that we call, in America we call, you add bells and whistles to it to make it fancier and everything, and then you can charge more money. Okay. So this is the example of, again, where you have prism, you have metal film, and then you have over here where a testing medium, and then you see that this is immobilized antibody in this case. When he grabs the antigen, remember this is lock and key kind of arrangement, fitting it, and then the angle changes. Angle changes from here to here. This change means if you are just sitting here and it changes, now the reflectivity goes up to this, at this angle. So your reflectivity goes up. And this is what we call sensogram. So you use that to detect. Is it clear enough to some of you who are learning for the first time? All right, you can ask me a question later. So let's look at another case of how we use metals to detect. So instead of film, if you have a nanoparticle of gold, what is the difference between film and gold? Film is extended. It's a nanometer in thickness, but it is long, many centimeters could be in the length. Okay? So it's confined only in this direction, and your oscillation is here. But when you use a nanoparticle, let's say spherical nanoparticle, then the electron cloud is confined in all dimensions, right? So what the physicists they like to call a zero dimension system. It's not extended. So here, if you have oscillation, if you use light to oscillate the charge, it can happen in all directions on the surface. And there is no angular dependence because there is no such selectivity to couple, but there is frequency dependence. Each metal in certain configuration will couple to light only of a given frequency that their electron cloud can follow. And that one is called localized surface plasmon resonance. Why localized? Because it's not a film. It is trapped in all three dimensions. Okay, so it's called LSPR, localized surface plasmon resonance. Okay, and that is very characteristic of this metal nanoparticle and what surrounds it. Okay, that frequency. So for gold nanoparticle, this occurs in the green, like about 525 nanometer light gets coupled in there, essentially absorbed, and then it gets converted into charge oscillation. Okay? You go to longer wavelength or shorter wavelength, it doesn't do the same. Okay? So what if again, instead of the film, I cover the gold nanoparticle with antibody, which is biorecognition. And when it captures the analyte on the surface, it changes the condition and it changes that plasmon resonance frequency, the wavelength. So it may not be 525, it might tend to 526. Okay? And so by change of that wavelength at which this resonance occurs, you can actually detect it. So how you detect resonance? Again, the same thing. If you take a nanoparticle dispersion or immobilize in the surface, and you shine light and change the wavelength of light, at the wavelength it couples, the transmission goes down because it's being absorbed by the nanoparticle. Okay? So you are doing absorption or transmission spectroscopy, and you look at what wavelength the light is being absorbed by nanoparticle. And when it detects the analyte, that wavelength shifts. So by monitoring the absorption spectrum, you can monitor it. So these are the two different tools. And we talked about this already. This is kind of showing the scheme of how you immobilize the capture antibody. Then you can have from analyte the antigen connecting, and you can detect, and you can, let's skip that, it's a little more complicated. You can also utilize not continuous film, but patterns of these micro pattern gold nanofilm, and each micro pattern may have one kind of antibody to detect one analyte, another one, another. So you have resolved into many different domains, and each can sense one analyte. So you can do multi-analyte detection, and that's an area is called plasmonic array. So we have array of these in the film, like here, and each one can detect one analyte. So you can do many analyte detection. Let's look at, we decided we are going to skip this one. So let's skip the photonic crystal. Somebody is interested in a gallery mode, right? Person is here? No. All right. So let's just skip that too. When we are trying to sense the organic dyes that you can use, or nanoparticles, can also play a very important role in the design of that. For example, not only do you want to detect DNA and RNA and profile the sequence or other chemicals, but you also want to monitor the what is called physiological parameter function. And what are these? Well, first pH. If you change the pH condition, the cell activity totally changes. That's why our system is buffered. It's buffered at certain pH. And if it goes beyond, like become more alkaline, more acidic, your functions can be trivially affected. Okay? So you want to monitor the pH also. Okay? The other one is oxygen level. And as you know, that oxygenation, if you get below a certain level, that's very, so you have to monitor, again, disease profiling, whether you have hypoxia. Hypoxia is, lower level of oxygen. And particularly, we'll talk about it, that the regions around tumor very often are hypoxic. So if you have a thick tumor inside, you have a hypoxic region. And if you want to treat that area, it's very difficult to treat, because that many therapies, like photodynamic therapy or radiation therapy, they are not very effective if you have hypoxia in that region. And we'll see how we treat that. Then you're looking at membrane potential. The membranes are charged. Neurons, their potential on the surface, it plays a very important role, and you want to monitor that. Temperature is very important, because our temperature, again, if you have too high fever, This could be dangerous. Or you have too low temperature, your body temperature drops, you need to, also it can be critical. So monitor that enzymatic activities. As you know, your organ function depends on certain enzyme level. By looking at liver enzymes, you monitor kidney function by looking at kidney enzymes. So you want to monitor the enzymatic activity, physiological factors. And so you can design fluorescence sensors, or organic fluorescence is very dependent on the pH of its environment, or in some cases oxygen. So those are oxygen sensors, or electric field. These are polarizable dyes that actually, when change of with electric field, fluorescence can shift, its value. Temperature dependence. You can also monitor an enzymatic activity. You can make them responsible to certain enzymes. So you can design dyes to sense all these. And again, as you will see in nano case, the beauty of nano is that in the same nano platform, you can put different dyes to sense different things. Okay? So here there are some dyes. So amine anthracene is a pH sensing dyes. So a spectrum is very much dependent on the pH. As you can see, from 9.5, which is very alkaline, it goes to very acidic, and you can see a change in the fluorescence spectrum. Okay, this is another dye. Then there is here there is a dye where not the intensity change, but the lifetime changes. And by doing lifetime imaging, you can map out the domains of different pH. Okay. This is the method that we developed for mapping temperature, and basically it talks about that different kind of absorption, that actually one absorption that goes from lower vibrational level to here, and the other one which goes from thermally activated vibrational level. Only thermally activated vibrational level can produce fluorescence. Okay, that's a longer wavelength. So if we take the ratio of these two fluorescence intensities, one excited by this higher energy photon, one excited by lower energy photon, then we can get the Boltzmann factor, the thermal population of this, and from thermal population you can measure temperature. So we use this probe to measure temperature of the cells. So these are some examples of how you can design dyes. We can talk about other dyes also if you wish. The other sensing is flow sensing. It's called flow cytometry. It's a very important tool in many clinical labs. They will have this kind of instrument. It's an expensive instrument, but it's a beautiful optical instrument. And it has a number of components which are engineering related, number of components that are related to chemistry, making probes, and then so let's look at what it is. So basic concept. So use cells. So this is cell profiling. You want to look at the cell samples. Let's see, the samples are, from a tissue taken by tissue biopsy. So what do you do tissue biopsy? You want to look at the cancer, and you look at in the image and you see some kind of growth, and you then, with incision, you take a little piece of tissue and you do biopsy, right? So one of the ways you could also diagnose whether it's a cancer cell or normal cell, normally if you take a tissue, and unless it is completely from tumor area, There may be some normal tissue, there may be some cancer piece cells. This is combination. So it's a heterogeneous population of cells. And what you want to do is how many of cancer cell you are going to see there. And that will tell you the stage of cancer that you are seeing. Okay, so this technique actually does cell profiling. It looks at the population of different kinds of cells and maps that. Okay, so basically you prepare a cell sample. So how do you prepare a cell sample? You take the tissue, you grind it, mix it into a buffer solution, and then extract the cells so that you have cells, right? And then what you do is that you can label the cells with an organic dye, fluorescent dye, or you can label it with nano emitters. We'll see quantum dots or something others. And so they're labeled by coupling to the surface of the cells, okay, through again antibody or antigen, in this case antigen that couples to that. And then the second one is that the suspension is flow through a capillary flow. Okay, so you are flowing it, but you want to make sure the dimension of the capillary is such, this is the trick, that only one cell at a time passes, moves. It's not like crowding up of 3-4 cells over here. Okay, one cell at a time. And that's what is called hydrodynamic focusing. How do you focus it to narrow a stream that only one cell goes? And remember, the cell dimension is like about 20 to 25 micron, it could be. Okay, and that's what is called more into fluid dynamics. So the engineers can devise this. And one of them is that you have a core that flows the liquid suspension of cells, and then you have another liquid outer, and that is called sheath of liquid, and that flowing outside, and that's what squeezes it, the inner one, to a normal flow. The two liquids don't mix. You need to make sure. Okay. So that's hydrodynamic focusing. So now the cells which are labeled, and they're going through this. Okay. And then what you want to do is you use laser light at certain point to interrogate the cell. Interrogate the cell, that means it excites these fluorophores on the surface, if they have it, and generate the emission coming out. Okay? So here you need a light and you need illumination optics to focus it to the dimension that it always recognizes the cell, one cell going through. It always interrogates each cell individually. Okay, so you design it so you look at each cell passing through this zone individually. Okay, and then you monitor optical response. So what are the optical response? One of them is the light may be scattered. And a scatter can be in whole 4 pi, all directions. So you monitor a scatter, a straight light coming through, and the scatter at 90 degree. So there are 2 scattering parameters. And then you monitor fluorescence of that dye. Is there any fluorescence coming, or what color? Okay? So that's another parameter you monitor. And then you analyze the data that you get through a spectrometer or a filter. You look at what wavelength of light is coming out. You monitor that through photomultiplier, detect there. And then you have a computer that gives you printout of how many cells it is detecting that have picked up the fluorescent label. Those are the cancer cells that are picked up, right? And the other ones, the normal cells, they don't have the right antigen to grab these, then they don't pick up that. They're not fluorescently labeled. So the labeled ones you detect unlabeled ones you don't, and you count them, how many of them are coming through, okay? And then you just, through computer, you make what is called histogram, or you can say what is called dot plot to give you population of cancer cells that you are seeing in here. And so you can count these, and you might say that may be very slow process, but now with fast data acquisition and computer, you can go to 5,000 cells per second. You can count very large number of cells. So you can do very rapid analysis of finding how many cancer cells you are, and detection limit is such that you can count 1 in a million cells. You can count by this technique, okay, detect. So eventually, also, what you can do is you have two different cell population, let's say. You can have many. I'm just giving example of two different, one normal and one cancer. But you can have many different kinds of cells. And you can label each of them separately, like this. And then when you come here, at this point, looking at fluorescence, it may direct this labeled one through one arm and unlabeled one through another arm. That method is called cell sorting. There are different ways of doing. One is mechanical, that shifts back and forth, one going this way and the other one moves to another direction. Or you have electrical, so the fluorescent one is charged and it gets pulled by electric field in another direction. Cell sorting. So you can sort out the normal cell versus cancer cell. And I have a company that makes flow cytometer, so I try to sell it see if in India they will be interested. They were not interested in the laboratory of cancer diagnostic. They were interested in animal farm, because you can actually separate the chromosomes, right? And then you can actually use the ones that produce female cows, select the cells that produce one gender, okay? So it was for that application rather than for profiling of cancer. So we didn't have a cell sorter, we were only like cell cytometry. So we didn't offer. But so this has application in many different areas, because basically the principle is to detect different kinds of cells and separate them if you want later. Okay, so these are details of new designs. Yes. Okay, okay, good. So we are good time at tea break, because some reason I'm thirsty, so I'd like to have some. So anyway, let me finish this. These are some fancier designs of. Normally, this is what you do in the train. You have laser light focus through here, and then you collect light and you separate them through different filters to different ports, and you monitor, as I said, forward scattering, side scattering, and emission, fluorescence, these parameters. And this is our company's design that doesn't use these mirrors, but uses fibers to separate. So they are more portable, and as I said, you have direct that forward beam, side scattered through side high angle or on the side, and then fluorescent. These are the parameters. Okay, then I'll talk about what is this plot. Let's take a coffee break. Or tea break, in your case. Go ahead.
This is for tea now. Tea break.
Yeah, that's what I'm saying. This is a break for tea, so please get up and have tea. So look, while you all are enjoying tea, it's okay. I think that what I sensed from some of the questions are constantly being asked, that you are very anxious to learn about nanoparticles and how you utilize them, what are its capabilities, what is the status of that. So I propose that I will skip most of the fundamental slides, just go through, and if there is a chemistry part, then I will go through that chemistry part. But all the physics and engineering and all these parts we will skip and get to nano today, so that we allow enough time for you to understand what are the promises of nanoparticle-based diagnostic therapy and what are problems that you need to address. And if you are developing a nano formulation for something, how you go about it, what is from a step A to B, B to C, and D, how you want to progress according to my view. And if the time permits, in the last lecture, we can always come back to some of these fundamentals. You may want to explain, or me to explain. You already have a lecture note, right? All of you have a note. So you can glance through that, see what I'm skipping. If there is anything you want to learn, we can always at the end, if the time allows, we can come back. Let's get back to the real thing that you are interested in. Okay? So let's take another 5 minutes for your tea. I will start. Any question, anything while we are having tea? And again, if the question is a nano, wait. Okay? Because a lot of you have come and asked, well, how are we going to use this nano for this and that? So let's get to that first. I admit the research in this area, if you want to have something that you can take from materials to characterization to testing, it may be an expensive research. But if you are talking about certain aspects of it that you want to develop and contribute, and hope that somebody else whom you can contact, work with, who do the other part, then it doesn't have to be very expensive.
ऑप्शन इबादा है क्या यहाँ पे? ऑप्शन इबादा
पूरा नहीं के ये छूट गया अच्छा कोई नाश्ता के ए बी ये करें पूरा लिखने के